Okay, questions? Lisa?
Like in some places, the chlorine would be like a, sorry, hold on, activating and deactivating. So which one is it?
It's deactivating.
It's deactivating.
Right, so chlorine or any of the halogens are deactivating because the chlorine is withdrawing electron density from the benzene ring. And so that's reducing the amount of electron density in the ring. And what we're talking about doing is we're talking about reacting a benzene ring with an electrophile. So what's going to make that reaction go faster is a more electron-rich ring.
Well, I misspoke. I meant resonance or induction.
It's induction.
Okay.
It's induction for deactivating. We'll deal with resonance later. It actually can do something with resonance, and we'll get to that. So it's deactivating by induction. But either way, what does it mean to deactivate the ring? It means pull electron density out so that this is not as electron rich, because the more electron rich it is, the faster it'll react with the electrophile. So push electron density in, you're going to make it go faster. Remove electron density, it's going to go slower. What else?
Sorry, this is a little last question, but for first reduction, how do you know where the two double bonds move if it's substituted?
Good question. So, Birch reduction on a benzene ring is sodium and liquid ammonia. Now it was the beginning of the semester when we talked about sodium and liquid ammonia before in the reaction of a triple bond. So the sodium and liquid ammonia basically creates a solvated electron that's going to add into the ring. In the end, we're going to remove the aromaticity and make a non-conjugated double bond. Okay. So that's the overall reaction. Then the question becomes, if I add an alkyl group to the benzene ring, where does it end up in relationship to the double bond? You don't have to memorize that per se. If I said, you know what, you're going to end up with the most stable product, where's the R group going to go? It's going to be attached to a double bond. So the R group is going to end up attached to a double bond to make that double bond more stable. So it's kind of a thermodynamically driven process. Now, if you have two alkyl groups and you can't quite fit them both to a double bond, and they were different, then you get 50-50 of each. But this is basically going to be a thermodynamic process. Thermodynamic process meaning you're going to form the most stable product. What else? Please.
The free hole craft, reaction with the straight chain. Did you do one of those? And there was like one that you had to use this pseudo craft for both of the problems, but so different.
So there would be Friedel-Crafts alkylation. So what is the product of that reaction going to be?
Be just in addition to that one, purple.
So it's going to be an isopropyl benzene.
How long did you do when you did your lecture video?
So how long would you like the chain to be?
How about something that's going to be understandable? Something like that's what I would like to.
Well, you just did. Potentially. All right, let's make it a 5-carbon chain. What's the product of the reaction going to be? Josh?
We still have the hydride shift. So,
I'm still going to have a hydride shift.
see, but I don't know, can you do multiple hydride shifts to get the carbocation in the middle? Or will it just still do just
I don't know. Let's poll the audience on that one. Can we do multiple hydride shifts?
No.
No.
Okay.
One of our rules is that when we do a hydride shift, it has to form a more stable carbocation. The second rule is you only get one shift. It's just, it would, if there were multiple shifts that were possible, it would just be utter chaos. Well, no, I mean, think about it from the standpoint of that. I mean, when you do a shift, you pay a price, right? To move a hydrogen or a methyl group from one carbon to the other, you pay a price in an activation energy. And in order to get back my investment, I mean, if we're making energy money, which is really what chemistry is all about energy, right? Politics is all about money. So if you want to understand chemistry, you need to understand the energy, and you can do the other in another class. But if you're going to go over an energy barrier to do the shift, you're only going to do that if on the other side you form a more stable product to get something out of it. Now, you'll get something out of it because Hammond's postulate says you'll lower the activational energy a little bit. So you'll get that, plus you'll get the energy being lowered. So in this case, what's going to happen is this. The aluminum trichloride is going to, the chloride's going to take its pair of electrons and give it to the aluminum. And eventually what's going to happen is this is going to become more and more delta minus, and that becomes more and more delta positive until that delta positive would add to the ring. Because we're still not allowed positive primary carbocations in solution. We're only allowed those gas phase, mass spec. That's it. So when the aluminum trichloride, I'll write the trichloride over here, comes and grabs a chloride from an ethyl group, you can say, but the ethyl group doesn't do a hydride shift because it can't. There's no more stable carbocation. So this aluminum keeps pulling the chloride off until the carbon becomes positive enough to add to the benzene ring. It never forms a true positive carbocation. It just gets to a point where now it can add to the ring. Same thing would happen here, except a competing process is for the hydrogen here to then do a shift to then give me a CH3, a CH plus, a CH2, a CH2, and another CH3. So in ethyl and methyl, you just keep pulling the chlorine off until it adds. But as the aluminum's pulling the chlorine off, at some point, the hydrogen's going to shift over, and you're going to get a secondary carbocation that then's going to add into the ring. So as far as every molecule, whether it's, what did this one do? This one took this group and made a methyl out of it. This one, I'm going to end up with a CH3, a CH, and then a CH2, CH2, CH3. So for that, for straight chained Friedel-Crafts reactions, I'm always going to get a methyl group here. I'm always going to get the secondary carbon there. And then this chain is going to be as long as what's ever left over. So any problem that I could give you is going to look exactly like that for a straight chained Friedel-Crafts. There are other Friedel-Crafts where you could have a methyl shift or a hydride shift, but they're not straight chained. Aaron? Well, think about when we first started talking about hydride shifts. The classic one that I know works is this one. So there's a popular, well, it's popular with me, organic 2 experiment where we take metaxylene and we treat it with tertiary butyl chloride and iron chloride. Okay. I usually do this in my sequence, in my second semester sequence, and then we take the NMR of the product, we take the IR of the product, and we try and figure out what the substitution pattern is. In other words, where did the tertiary butyl go? Did it go to A? Did it go to B? Or did it go to C? Right. And we're not up to ortho para and meta activating groups. We just talked about that in the video. It's just activating, deactivating, right? So where the tertiary butyl group would go, it either goes A, B, or C. So that's what we try and figure out by NMR, and then by using a very narrow range of IR. Okay. So tertiary butyl chloride is going to easily react with the iron trichloride, and it's going to form a tertiary carbocation, right? And that's Friedel-Crafts alkylation. So when I think I taught this for the first time when I was at The Ohio University a long time ago, a very long time ago, like 24 years ago. I'm sure things have changed since then. Like they're all young scholars down there, and Thursday night's not young adult night anymore. Although I passed by the Campion dorm at 10:30 last night. Apparently Thursday night's young adult night here at John Carroll, from what I saw.
So wait, you're saying you've never written on KVD?
What?
You've never gone on KVD?
Yeah. Well, I don't think that I've heard I don't need to know.
You do that.
You have to try it at least once.
No. But I digress. So the first time we did this, I grabbed the isobutyl chloride instead of the terse butyl chloride from the stockroom. And so about halfway through the lab, a student said, hey, we're using isobutyl chloride and not terse butyl. So do we have to start over again? And I said, no, it'll be fine. And then they didn't quite believe me. So I said, no, it'll be fine. You'll get terse butyl. And then they kept pushing. So I said, well, good. That's going to be your post-lab question, is to show me why everything's going to work out okay. Because what happens is that this hydrogen shifts over, kicks off the chlorine, and you end up with the terse butyl carbocation. So I know that one works because we've done that by mistake, but we still did it. So whenever you're trying to do Friedel-Crafts, you can have any rearrangement occur. So it's just like, where did we see this before? We could have seen this when we tried to react that alkyl halide with water. And I said, write the rearranged product. So we had that concerted shift, leaving group leave to give us a new stable carbocation. So the same thing's true with Friedel-Crafts. Okay. So the issue is, there's one example, and I think there's probably more on the practice problems for Monday. But the problem with trying to take a straight chained alkyl halide and making a straight chained benzene ring is that will happen once you get to propyl and beyond. So you cannot make a straight chained alkyl benzene by using Friedel-Crafts alkylation. So that's where we get to the reaction where you say, okay, if I want to do that, what do I need to do? Now I need to do Friedel-Crafts acylation. And FeCl3 and AlCl3 are interconvertible. So what happens here is I add the benzene ring, to the benzene ring, the carbonyl, which will not rearrange. And so now I need a way to reduce that carbonyl down to a CH2 group. And a couple of reagents, the Wolff-Kishner, the Clemenson reduction, both of those will then reduce that basically phenyl ketone. When benzene ring itself is used as a substituent, it's called phenyl, PHENYL. Benzyl is a benzene ring plus the CH2. So that's not what we have here. This is a phenyl. So we call that a phenyl ketone. That then gets reduced down to the straight chain alkane. So that's why we're introducing things like Wolff-Kishner and the Clemenson reduction, because this is the only way to add a straight chained alkyl group to the ring. Because if you try and add it from Friedel-Crafts, it's going to rearrange. Brian?
Any advantages to Clemenson versus Wolff-Kishner, or did they do exactly the same?
I think one of them actually is not. One of them is only for phenyl ketones, and the other one will work with any ketone, but I forget which is which. So they're both equivalent. Sarah?
So, there's two classical reagents that can be used for that last zero.
Yeah. So you can use zinc, mercury, HCl, heat. Or you could use N2H4, KOH, heat. And this is Clemenson. And this is Wolff-Kishner. But both will work. And that's really their only two functions of those two reagents, is to reduce phenylketones. So does that make sense? So if I give you an alkyl halide that could rearrange, I'm again going to have to tell you, but I will not tell you if you try and add a straight chained alkyl halide, because that always rearranges. So that one I won't tell you to rearrange. This one I might have to tell you to rearrange. What else? Go ahead.
I was going to ask you to do a Wolff-Kishner, but
There's no mechanism. Well,
there was one
there is a mechanism for Wolff-Kishner, but we're not going to go into it.
I don't know if you started it. It was just
Yeah, I think I started it by showing how the N2H4 produces what's called a hydrazone, but we'll talk about those later on.
okay. Well, what about the methyl group that's the director and tells the electrophile where to go? Is that what we're going to talk about later on as well?
Yeah, I think there's a whole lectures coming up on that. Sarah?
Going back, what was the point of that benzene ring in the top left?
What was the point of that benzene ring? That was the whole behind-the-scenes story of the experiment that we were doing at OU and we used to do here. So the whole idea was we were adding a T-butyl group to the ring, and we were trying to figure out where it adds. Maybe I'll come back to that later because it's not what you would predict. And I remember, I think, having an argument about that the first time we did it here with my senior colleagues. Because I'm like, they're like, it's going to go there. And I'm like, no, it's not going to go there. So that's what we were trying to do. And the whole point is isobutyl would do the same, would produce the same carbocation as tertiary. What else? Let's see. I've got extra problems. Okay. Oh, wait. There's two ways to make straight-chained alkyl benzenes, according to this problem set that I have. One is to do Friedel-Crafts and then do Clemmensen or Wolff-Kishner, and then there's one more. So I guess I must have lied about there only being one way to make a straight-chained alkyl benzene. And I didn't lie. That requires intent. So I had no intent to deceive you. But is there another way that we could couple like a butyl group and a benzene ring and make a straight chained alkyl benzene? What if I take this benzene ring and I turn it into a bromobenzene? Do we know how to do that? We should. Then what if I said I'm going to turn that bromobenzene into a organolithium? Do we know how to do that? We should. And then I said, you know what? I'm going to react that with butyl bromide and couple those two together to make my butyl benzene.
With these problems, do you have a choice in which way you want to go about getting a final product, or?
It depends. If I just said go from here, if I just said go from here to here, yes, you could choose any method you want. But what I'm showing you is that there's another way to do it beyond the Friedel-Crafts and then the Wolff-Kishner-Clemenson. So what am I missing? Aaron? Yeah, I know. You get half credit on that. Depending on where I'm at in the grading process, probably towards the end. No, we know that we need the reagents. So what specific reagents do I need to basically do this part? That part. What? It's a reaction that we've seen before.
Yeah.
No. What? I need to add something. Then they'll couple together. Aaron? No. There's no anti-Markovnikov. There's no double bond here. I'm coupling two alkanes together. No. Brian? How am I going from here to the final product here? So I've got an organolithium, and I would like to couple that to an alkyl halide.
NGS.
No. Sort of. That's what the organolithium is. So if I said coupling, you might think Wirtz coupling, right? No. Wirtz coupling was a long time ago. But Wirtz coupling was what? Wirtz coupling's when a Grignard coupled to the alkyl halide, but that was an unwanted process, right? It wasn't very efficient, and it killed our Grignard. But then after that, I said, probably more than once, you know, it would be really nice if we could take a C- and we could form a carbon-carbon bond off of it. So if I can't do that by Grignard, we had this other reagent that we could do it with. See, you stop right there. So I could add copper iodide. And what did that do? If I add copper to the organolithium, what does it do? It created that which is called a close. You're missing the other part of it. It's a lithium cuprate. Right, Gilman reagent. So I can make it a straight chained alkyl benzene if I make my Gilman or I make my lithium cuprate out of benzene. I can attach any halogen I want, and it'll just couple the two groups together. And so I can put any alkyl benzene on the ring by using a cuprate.
Like more of a general question, but why is there like a parentheses with a 2 around for that?
Because what's happening is this is a +1, this is a +1. I need 2 -1s to balance it out. Okay. So the idea is that we've seen this reaction before, but if you think about this in a more general sense, I could use this to put any alkyl group I want on the ring. And I don't have to worry about any kind of rearrangement because its mechanism isn't suitable for rearrangements. We're going to come back to that because there's a whole series of reagents that allow me to add alkyl groups to benzene rings called Suzuki coupling and Heck coupling, and they're all important because they let me put my alkyl group on that ring in one step. So these methods have actually supplanted doing Friedel-Crafts then reduction. Why do that when you can just do this coupling reaction in one step? And then there are actually some more, and there's some other heavy metals that can go, or transition metals that can go in there that actually I can run this reaction in water, which would be far more environmentally friendly. Ring?
So what you're saying is that you can combine the lithium and the bromine through the CUI. Like, is that what the whole
Well,
point of that was?
I'm converting this. I know how to make that, right?
Right.
Oh, I forget. What am I adding up here? BR2 and FeBr3. I heard NBS. No. I heard BR2. No. Not by itself. Right? If I give you benzene ring plus BR2, it's no reaction. If I give you benzene ring plus NBS, it's no reaction. I would never have thought to do that, but now I see I can trick people into that. It's not my job to ask trick questions, is it? So then how to get from BR to lithium? How to get from bromobenzene to the organolithium? What'd I add? Lithium. Doesn't matter. No, you need two, but the stoichiometry. So the point of this is, if you want to make an alkyl benzene, you could go through Friedel-Crafts alkylation, and that'd be great if the group you want to put on there isn't going to rearrange. But if the group you're going to put on there is going to rearrange, you could use this as an alternative, and then use the lithium cuprate to couple the benzene ring with the alkyl group.
Is there a way to do the same reaction, but instead of using lithium, you use magnesium?
No, lithium, it requires lithium cuprates.
Okay.
And there's probably a reason why, but it's magnesium. We treat magnesium and lithium interchangeably, and they're not. So only lithium goes with the copper. Kevin?
Why do you need the copper? Why doesn't the organolithium SM2 the bromine?
Because it just doesn't.
Okay.
Those molecules don't undergo SN2. When I make a copper out of them, I actually change the mechanism to something that looks more like a free radical mechanism. It's called a single electron transfer reaction, which quite frankly is like, well, isn't every reaction transferring one electron at a time? But it depends on the speed. So these are more, those reactions, these are more of single electron transfer, and so that's why they couple together. Which kind of makes sense because we use coupling in free radical reactions. So it's an offshoot of that. Okay.
So do you need both the BR2 and the FeBr3?
Yes. You have to have the FeBr3 to make the Br2 into a full-blown Br+, because only that's strong enough to add to the benzene ring. So just Br2 isn't strong enough.
Is that the only other thing that can be with the BR2 or too strong enough to add?
Or AlBr3. It's usually either iron or aluminum. It's something that basically rips the Br- off and leaves the Br+. So it's either aluminum or iron. Any other? Now your side chain, once you put a side chain on a benzene ring, which now I can do 2 ways, 3 ways, Friedel-Crafts reduction, Friedel-Crafts alkylation, Friedel-Crafts acylation with reduction, lithium cuprates. Once I put my side chain on the benzene ring, I can do anything with that. And by anything, I mean everything that we've learned from now back to the first day of class, last semester. Right? So I could say, hey, I want to react this now with NBS. Am I allowed to react NBS with that alkyl benzene? Yes. And what's going to happen? Well, what does NBS do? It adds a Br, or better, more precisely, it substitutes a hydrogen with a Br. So where would you like to put that Br in this molecule? What hydrogen would you like to substitute for? There's a right answer. So you want to add the bromine in the ring?
It only adds one bromine.
Adds 1 bromine.
Would it add to the benzoic carbon?
Close. The benzylic carbon. So this is going to do free radical halogenation, which means it's going to pull off a hydrogen that gives me the most stable radical. What's the most stable radical? The benzylic one. And so where does the bromine end up? On the benzylic position. So the benzylic position is the important one for a side chain, because that's where you're going to add a halogen. And then what could I do? Anything. I could replace the bromine with an OH. I could form a double bond. Let's say I wanted to form a double bond. Where do you want to form the double bond between? Where you want to put the double bond? B and C? I want to put it between A and B. Why not? No hydrogen on A, so there's no, it's not a beta hydrogen. Here.
Isn't there resonance in that ring? So the double bonds are always.
Well, there's resonance if I do what? Well, if the bromine leaves, I end up with a positive charge. And is that stable? No. That's a benzoic carbocation. That's super stable, right? It's not aromatic stable, but it's pretty good stable. So then the question would be, if I'm going to form a double bond, this is my alpha carbon, this is my beta carbon, and that's my beta carbon. So can I form a double bond between A and B? No. Why not? Because there's no beta hydrogen to lose. And if I did, how many bonds would be on A? 5, and that's a no. You can't have 5 bonds to the carbon. Now, you're all like, oh, I would never do that. But this is why I don't draw circles inside the ring very much. Because the circle makes you forget that there's a double bond there and there's no hydrogen. So the only double bond I could form would be between B and C. So what reagent would I use to form the double bond between B and C directly? Because an E1 is not very efficient, right? So what would I use to form that double bond? What reagent do you want to use? N NH2 minus? Tertiary butoxide? Does it matter? No, it doesn't matter, because if that's my alpha carbon, there is only one beta hydrogen. So there's only one hydrogen that's accessible. Whether I use NH2 or tertiary butoxide, I'm going to get that double bond. Okay. So then I'm going to add H plus H2O to that double bond. So where's the H and the OH going to go? OH on B, H on C. We all agree with that? What if I changed my molecule a little bit and said, I'm going to add H plus H2O to that double bond. Where's the H and the OH going to go? OH on A? No? OH on B? So after I add my H plus, my choice is between these two, right? So which one's more stable, top or bottom? How do people say top is more stable? Bottom. See, that's where the clickers would have, that's where the cards would have picked up a few B's. So what's more stable, the benzylic or the tertiary? Benzylic. How do we know that? Because that's where we ended class on Wednesday. No, I haven't done that experiment. I would like, well, here's another way to do that, to figure out which one of these two carbocations is more stable, and it might be even easier. I make this molecule, or I buy it, and then I add H plus H2O to it, and I figure out where the OH went. Right? And either I get a mixture of products, which then I can find out which is the major product, or I get exclusively one product, and that'll tell me which carbocation is the most stable. But that's what I was trying to show you at the end of last class, was basically in terms of our rankings, the benzylic is more stable than tertiary. I would then call probably allylic would probably be about the same as a tertiary. So I haven't seen any rankings of that, but there's lots of ways we could do that. Right. So that was, the whole purpose of this was to see if you remembered what we did on Wednesday, which wasn't bad. I would have, I don't know what I would have put the over-under on, but so remember that. Okay, I've released the video and stuff for Monday, so you can go ahead and watch that, do the online quiz. There are practice problems for Monday up here that you can get, and then if you start reviewing over the weekend and you have questions for Monday, by all means bring them. And if you're shy, there's a stash of 3x5 cards you can write your questions out on.